Astronomy is awesome. Quite literally, it is awesome. Aside from the forays that we've made into our own solar system, everything we know about the universe, from the formation of stars to the explosion of stars as they die, to the fireworks when galaxies merge, to the edges of our universe at the Big Bang, we know about because of light, because accidentally we were in the right place for photons, little packets of energy, to hit our eyes or our telescopes or our cameras. That's quite amazing. And that makes astronomy quite unique amongst the sciences. We can't travel to these things. We have to stay on our little island of the Earth, or just outside it, and receive all of this information in little packets, little precious photons, each of them with their story to tell. And it's our job as astronomers to decipher that story and to expand the boundaries of what we know about the universe. For millennia, people looked on the heavens and they saw something that was constant. The stars that they saw in the night didn't appear to change. And if they did change, they were one-off events like novae, or maybe even comets. There were regular features in this backdrop of planets and the moon. These stars were so constant that people told stories, and the figures in those stories they threw up into the stars so generations would have that reminder. That all changed when the telescope was invented. We could see further and fainter than we'd ever looked before. And we saw that the story that the light was telling us was actually far more complicated than we ever imagined. Galileo turned one of the first telescopes onto Jupiter, and that totally changed his worldview. He viewed the solar system totally differently after that point. He saw Jupiter as a microcosm with its own moons going around it, and he thought, that's what the solar system looks like. But when we had these basic telescopes, and I couldn't resist using this deliciously steampunk picture behind me, how did we tell that story? We only had our eyes. We build bigger and bigger telescopes, but unless we have some way of recording that information, really the story is limited. People used to draw all manner of astrophysical objects in the night sky. This is one example of a spiral nebula that Lord Rosse, the 3rd Earl of Rosse, drew in 1851. When a bright spark decided to plug a newly invented camera into the back of a telescope, then something significant happened. That picture became something like this. And it wasn't a huge step to start measuring the distances to these things once we could record that information in a way that other people could look at and tell the story. We knew that these spiral nebulae weren't nebulae in our own galaxy, in the Milky Way galaxy, that they were distant things. They were galaxies like our Milky Way. But these photographic plates were limited. We've only got intensity information there. There's no color information. And with the digital age, we came up with clever ways to record not only the intensity, but the color, and composite those things together. So now we have a new story for this spiral galaxy. You can see here that it's got blue, red, and yellow parts. Those all tell a different story. The dark parts in that tell of a story about cosmic dust, things that are blocking light. The blue parts and the red parts are telling about oxygen and hydrogen gas. And that tells us about the dynamics of that system. But that technology came at a price. If you live in a town or a city anywhere in Northern Europe and in large parts of the world, you'll be familiar with light pollution. Wales is actually probably about 90, maybe 80% dark skies. But unfortunately, I live in South Wales, and you can see from this map that South Wales actually makes up for the rest of the dark skies. The rest of the UK is probably the opposite way around. It's probably 20%, maybe 15% dark skies. This means a big problem for doing astronomy. This is an all-sky camera. This is a fisheye lens on top of an astronomical camera that we installed in the physics department in the city of Cardiff here. This is 3:30 in the morning on a beautifully clear night. Hands up if you can see a star. You can't see any stars, but you can see plenty of unnecessary streetlights. Oops, you can see unnecessary streetlights here. It's 3:30 in the morning. Why do you need those streetlights and building lights? Lady Loon is actually in this picture. Can anybody see the moon? No, because she looks like another streetlight. There she is, there. So, as astronomers, we put telescopes at the top of mountains, in remote locations, all across the world, away from the glare of city lights. We put them on top of mountains so that they're above the layer of clouds as well, which is, as anybody who lives in the UK know, half the battle. This is, I have the great pleasure of going to this place. This is Haleakala on the island of Maui in Hawaii. And I visited this little observatory here. So everything that you can see on this mountaintop is an observatory. This enormous thing here is owned by the US military. I find it quite strange that they have the biggest and the shiniest of all the things on the top of the mountain. And from that side, this is what that all-sky camera sees. It's a totally different picture. Now you can once again see the story of the cosmos unfolding in front of your eyes. You can see the beautiful line of the Milky Way, the dark patches of the cosmic dust in our own galaxy, the light patches of the stars. You can see individual stars and individual constellations. It reinforces that this is a place that you can do astronomy. But it's not always that simple. Sometimes it snows in these places, and this is the same observatory in the snow. So if you have one telescope at one location, and it snows, or worse, then you've got a problem. If you've got a blizzard happening and you've put all three of your telescopes on the same mountain, that's even worse. And it's such a shame, because you've invested a lot of effort in putting these telescopes into these fantastic, astronomically great locations. So for the past 10 years, I've been working with a group of colleagues from California to put telescopes in remote locations all over the globe. These are all the locations that we've decided to put them. They're all far away from city lights. They're all at the top of mountains or at high altitude, so they beat most of the clouds. And you'll notice some interesting things about them. They're arranged in the north and the south. To get the full story of what the cosmos has to offer us, you have to look in the north and the south, because the southern skies are different to the northern skies. If anybody's ever traveled to the southern hemisphere, you'll know that they don't have a pole star. We have, in the northern hemisphere, we have Polaris, which we can identify as true north. But in the southern sky, they don't. And the southern skies have loads of unexpected delights for us to view. So we have telescopes in the southern hemisphere. We have them spread out across the globe because, wouldn't you know it, astrophysical phenomena don't pay us the convenience of happening when it's dark at where your observatory is. So we spread our telescopes out so that if something exciting happens, we hope that we've got a telescope in darkness that can snap it. We also have lots of telescopes. We have big ones like this, and that's the inside of that clamshell that I showed you earlier. It's a huge telescope. Well, I say huge. It's huge by my standards. It's not as big as some telescopes out there. It's 2 meters in diameter, the primary mirror. That means that the whole telescope is the size of a double-decker bus. It can slew around the sky in about a minute, so it's pretty nimble for such a beast. We have 2 of those. And for the past 10 years, we've been using those to do exciting science. But in the last 2 years, we've been constructing more telescopes, smaller ones. These 1 meter class telescopes, again, the 1 meter is the size of the primary mirror. They're the size of a family car, and they can slew around the sky in a matter of a few seconds. We've got 9 of those, and for the past 2 years, we've been pushing them out the door and putting them in those remote locations that I showed you earlier. And very excitingly, we've got these little fellas. They're about the size of Dusty Bin, for those of us of a certain age, or for those of us of a geeky persuasion, R2-D2, so to about that big. All of these telescopes are robots. Now that's something that's incredibly significant because I showed you loads of locations. If I wanted to use each of those telescopes, firstly, I don't want to go to all of them because to get to Hawaii takes about a day from here. If something exciting happened in the night sky and I got on a plane straight away, odds are it had finished by the time I got there. So I could employ people to live at the telescopes. But then that's very wasteful. So we make them robots, and that means that we don't need to have specialists at the telescopes. The specialists can be wherever they are and remote control these telescopes. So we've got 11 of these. Soon we'll have a few more. Actually, there's a little telescope like these 0.4 meter class telescopes on a boat on its way to Chile at the moment. And that's full of exciting prospects because I'm really hoping that we can use that telescope with school children in Wales, in primary schools, an audience that's often overlooked when you do astronomy engagement. But a key to all of this is having a robot overlord, is having a robotic brain or a cyber controller. This makes our network very different to other networks that exist. This cyber controller, I tell this cyber controller what I want it to observe. I don't tell the telescope. I don't really need to know where the telescope is. I just say, I need a picture of the galaxy Messier 51, and I need it by Tuesday. Or, there's an exciting phenomenon happening now. Whatever resource you've got, put it on this source. And that's what the cyber controller's job is. It takes mine and everybody else's requests and puts them into some sort of nightmarish, multi-dimensional Tetris game and farms them out to all the telescopes all around the world. Now, I find Tetris a pretty difficult game. I'm not particularly good at computer games, as you can probably gather. Tetris, for me, is quite difficult, lining all those things up. Imagine you've got that in multi-dimensions, with new things popping in all the time. That's what our cyber controller has to do. And it does that job very well. So now we move into a realm of astrophysics on demand. Everything's on demand now. So we can have astrophysics on demand. You have a computer, you have an internet connection, you can talk to the cyber controller, you can talk to the adaptive robotic scheduler. That's what its proper name is. I prefer cyber controller. And you can say, I want a picture of M51. This is the spiral galaxy I showed you earlier. It's called the Whirlpool Galaxy. This was taken with 10 hours worth of observing on some telescopes on our network. I don't really need to know which ones. If I'd gone to that telescope, I would have had to waited there for 10 hours and just pressed, yes, new filter, new exposure, over and over. But I just told the cyber controller to do it, and it did it. And then my friend BJ did the image processing, and it turned out beautifully. Another example is this, Thors Helmet. This is in our own galaxy. There's a star in the center that's very hot and very bright, and it's surrounded by gas. Because it's very hot and bright, it's blowing out a bubble. And that's what you can see, a stellar wind bubble. It's blowing out this bubble, and it has two wings that you can see on either side. Now, the Marvel films that you probably watched recently, Thor doesn't have a helmet with wings on it. I think it probably would have made him look a little bit camp, which is why they left it out. But the original Thor had a helmet with wings on it, and it looked like that. Now, that's pretty pictures. That took about 20 hours to observe that. But we want to do science. We want to unravel the story of the universe that light is telling us. So what can we do? Well, here's another picture of a galaxy. But one of the exciting phenomena that happens continuously in the universe are exploding stars, violent deaths of stars that are way more massive than our own sun. And here's one of them. There it is. It looks quite uninteresting, really. But one day, without warning, this star exploded. Bad news for any planets that were going around that star. This star, if you look at it, looks about as bright as these stars here. Those stars are in our galaxy. That star is in a galaxy 1,000 times further away than the closest star in our galaxy. And it's as bright as the ones that we can see in the foreground. That's an explosion that we wanted to watch as it happened. So we got the network onto it, and it observed it as different sites went into daytime, other sites came into nighttime and picked up the observations. Here's another galaxy with a supernova in it. these fantastically bright things. At any one time, we're monitoring 20 supernovae in distant galaxies. In the last 2 years, since we've been popping those 1 meter telescopes out through the door, we've followed up and characterized 180 separate supernovae. Other things that we look at, other transient phenomena, asteroids, near-Earth objects. This is a time-lapse of about 16 hours worth of observations of this asteroid, again from multiple sites. Asteroids have the inconvenient property of sometimes heading towards the Earth. So you really want to know where they are and monitor them, because sometimes they not only go around the sun, but they also come towards Earth and they change course, because there's very massive things in the solar system, like the sun and like Jupiter, and that causes problems. It's like a solar system billiards set. These things change all the time, and you want to monitor them. You want to know where they are and if they're coming towards us. This one was coming towards us. It's only 30 meters in diameter. I say only. That's fairly small. That's at the limit of what we can observe. But it passed 4 Earth diameters from the surface of the Earth. It passed between the orbit of the Earth and the Moon. It passed actually 10 times closer than the Moon is. Now that had no danger of hitting us, ever. But if one was going to hit us, we'd want to know about it, and we'd want to be able to study it as it appeared. And that's why a robotic telescope network is really, really valuable. It comes into its own with this. Comets as well. Comets are beautiful things. But they, like asteroids and near-Earth objects, hurtle in towards the inner solar system. So we want to track them. Here's another picture of a comet. Now, everything I've told you about this being a robotic system, it lends itself to anybody using it. You'll notice the name on here, Dario Breen. Yes, it is the comedian Dario Breen. He used our network to observe this comet, and then he tweeted this picture. That's astronomy communication I could never hope to have done on my own. It opens up a whole new idea of what you can do. You can do fantastic science. You can unravel the story that light is telling you. But you can do it not with professional scientists. You can do it with a classroom full of kids who've never done this sort of astronomical investigation before, who are in Hawaii. You can do it with high school kids who are presenting at a science fair somewhere in the middle of America. You can do it with high school teachers who've become a little bit bored with their normal curriculum. And so we've been piloting. And by the way, that girl's saying, OMG, there's an asteroid in there. She really did say that. We've been piloting using these telescopes with school kids, teachers, with amateur astronomers over the past 10 years in 39 countries. Mixing in with the professional astronomers, it's hard to put a number on how many people we've actually reached, but we reckon it's about between 10 and 20,000. And that's in the last 10 years. In the last 2 years, I said we've put more telescopes out there. What I really want to do is now fill in this map, particularly this bit and this bit. Looking at the developing world, you can have a fantastic opportunity for capacity building, for exciting and inspiring people to look beyond their own horizons by looking towards the heavens, by doing inspirational projects that they can do, not with fancy equipment, but with a Raspberry Pi and a 3G connection. You need an internet connection and a computer, and that's it. So in the last minute that I don't have, I'm going to show you a visualization I did especially for you guys of everywhere that our telescopes have been looking in that 2-year period. Blobs show exposure time. Every frame is a day. So the bigger the blob, the longer that exposure time on that patch of the sky during that day. The colors represent the different sites that we used. So this is just our 2-meter observatories to start with. And that's where our 1-meter observatories are. That's a map of the sky. Remember, each frame is a day. The day counter appears in the corner. So with a global telescope network, we really can keep you in the dark. But actually, I wanted to put a positive TED-type spin on it. And I like to think that I'm always looking up. Thank you.